Hi, welcome to Chapter 13 on the atomic nucleus and nuclear physics. In this first part of the lecture, we will be looking at properties of the atomic nucleus. Before we get into the lecture, I'd like to point out a few of the many applications of nuclear science. One of the most important applications of nuclear physics is called nuclear medicine, and two of the main branches of that involve radioactive tracers and radiation therapy. Radioactive tracers involve injecting a controlled amount of radioactive substance into the body that targets a specific area of the body, and it allows for very high definition enhanced imaging of the inside of the body. And radiation therapy is used to basically target cancer and tumor cells to destroy them. Geology, archaeology, and even astronomy rely on a technique called radiometric dating, in which radioactive isotopes are used to determine the age of different layers of sediments, for example, in geology, or in archaeology, different artifacts can be dated. For example, if something is found in a cave, we can figure out how old that object is. And in astronomy, likewise, we use it to determine the age of the planets in our solar system. The atomic nucleus contains an enormous amount of energy, and that energy can be tapped and harnessed to produce electricity. So we'll learn about how this works in part 2 of this video when we briefly look at nuclear energy. And nuclear physics actually got its start with the development of the so-called nuclear or atomic weapons in World War II. We will also very briefly look at those in part 2 of this video. So this chapter is broken up into two parts. In this first part, we're going to look at the atomic nucleus, sort of introduce it, and look at the general properties of the nucleus. We'll also look at isotopes, the strong nuclear force which holds the nucleus together and is the source of all of that energy that can be released. And we'll also look at something called nuclear binding energy. In part 2 of this lecture, we'll look at radioactivity, half-life, fission, and fusion. So in this chapter, we're talking about the nucleus of the atom. And let's start by just getting a general sense of the scale or the size of the nucleus compared to the atom. Now, we learned in the last chapter that atoms are, of course, extremely small. We can't see them because the wavelength of light is similar to the wavelength of the atom. So a typical atom might be something like 3 × 10 to the minus 10 meters in diameter. So this would be the clouds or shells of electrons. Buried deep within the center of the atom is this tiny little speck here that really wouldn't even be visible in this image. It would be microscopic if this were the actual size of an atom. And this is the tiny little nucleus. The nucleus is something like 30,000 times smaller than the atom in diameter. And within this nucleus is basically a collection of protons and neutrons, and that's what we will be studying in this chapter, the behaviors of this atomic nucleus. So the atomic nucleus consists of two particles, protons and neutrons. So the number of protons is called Z, which stands for what is called the atomic number. And the number of neutrons is called the neutron number, and we use the letter N for that. There is also something called the atomic mass number, A, which is just Z plus N. So A is the total number of protons and neutrons, which are sometimes called nucleons, which just means a particle that's in the nucleus. And since there are only two particles, protons and neutrons are sometimes called nucleons. Now, there's a little bit of notation here that we're going to use in this chapter, and the nuclear notation goes as follows. The letter here, C, is the element symbol. In this case, C stands for carbon. The atomic number, which is, remember, Z, that is put out in front and down below. So for carbon, carbon has 6 protons, so that 6 goes down here. This particular brand or isotope of carbon is called carbon-14, and this 14 up here is A. And remember, that is the atomic mass number, which tells us the total number of protons and neutrons. Now, this notation here with the 14 on top, the 6 on the bottom, and both of those numbers are out in front of the C, is somewhat redundant because carbon always has 6 protons. In other words, what makes carbon carbon is the fact that it has Z equals 6. So this 6 is redundant, so we really don't need to show the 6. So oftentimes we'll just see the C here with the 14 up here, which tells us the atomic mass number. And this is also written out and pronounced as carbon-14. So if we look at a periodic table of the elements, remember we saw this in the last chapter, if we take a specific element, for example, here's carbon number here. Carbon is element number 6, so that 6, remember, is called the atomic number, which tells us the number of protons. The C, of course, is the chemical symbol. And underneath the C is the actual name of the element, carbon. And then this number below here, the 12.0107, is the average atomic mass. And this is something that we're really not going to deal with in this chapter. It's basically an average of all the isotopes that are found, weighted according to their how abundant they are. But you can see that basically carbon has an atomic mass of 12, and that's the most common carbon is carbon-12. We'll be referring back to this table throughout the lecture, but basically the most important thing is that for all of the elements, the number above is the atomic number. For example, germanium here is atomic number 32, which tells us there are 32 protons. So let's go ahead and do some examples just using what we've learned so far about Z, N, and A, the 3 numbers that describe a nucleus for one of these elements. So I've put this a little key here for our notation to just kind of help our memory, and I've also included one little section of the periodic table over here, which we can use to answer these questions. So question number 1, how many protons does carbon-14 have? Well, what we have to do here is look up carbon on the periodic table, and we see that carbon is element number 6, as we've said, and so we have Z is equal to 6 protons for carbon-14. Question number 2, how many protons does nitrogen-14 have? Well, so we have to find nitrogen. It's right here, and you can see that nitrogen is element number 7. So nitrogen has 7 protons. Now, number 3 says, how many neutrons does carbon-14 have? Well, we have carbon-14, which is shown right here. Remember, this number down here is the number of protons. This number is A, which is the total number of protons and neutrons. So the neutron number is equal to A minus Z. So we have 14 total minus 6 protons gives us our answer, 8 neutrons. And finally, a similar question, how many neutrons does oxygen-18 have? So the neutron number for oxygen, again, we're going to take A minus Z. So A is 18, because it's given right here, and we have to find out how many protons oxygen has. So we find oxygen in the periodic table, and we see its atomic number is 8. So we're going to take 18 minus 8, and the answer then is 10 neutrons. Let's look at a few more of the basic properties of the nucleus. We already got a sense that the nucleus was extremely tiny, even compared to the tiny atom that it sits inside of. Another way to look at this is if we tried to make a scale model of a hydrogen atom, all right? Now remember, a hydrogen atom is very simple. It just has a single proton for the nucleus, and it has a single electron that orbits around the nucleus. However, if we wanted to make this to scale, let's say we chose for our nucleus a marble, all right, that's our proton, a marble, and we set it in the middle of campus at Cal State San Marcos. Well, the electron would actually be so far away from that marble, it would be off campus, and the electron would be orbiting way out here. This is our campus map in the background there. So what this tells us there is that atoms are almost completely empty space. The amount of space between the tiny little nucleus and the electron is enormous compared to the size of the nucleus itself. So even a piece of solid metal, like a solid piece of iron, is 99.9999999, and it keeps going, percent empty. All right, so solid materials it's kind of surprising to think like a piece of rock or a piece of metal is actually almost all empty space. So all of the mass of like something like iron is concentrated in this tiny little nucleus because the electrons are very, very light compared to protons and neutrons. So almost all of an element's mass is concentrated in this tiny little nucleus. So the nucleus is extremely dense. Its density is billions of tons per cubic centimeter. And obviously nuclei are very small. Even the largest nucleus, one of the largest, is uranium. It's only about 14 femtometers in diameter. This is 10 to the minus 15 meters. As I mentioned before, the actual nucleus here is anywhere from 30,000 to 50,000 times smaller than the entire atom in terms of its diameter. Let's now talk about isotopes. Isotopes are basically nucleus or nuclei which are the same element, meaning they have the same Z or proton number, but they have different neutron number and therefore different atomic mass number, A. So we have the same number of protons, but a different number of neutrons. So isotopes have the same chemical properties because chemistry is due to the arrangement of the electrons in the atom. Chemistry doesn't really care about the nuclear properties, but isotopes will have very different nuclear properties. In other words, some isotopes may be stable and others may be radioactive, which is something we'll talk about later in part 2 of this lecture. So let's see what we mean by isotopes. Let's look at some examples. So in this picture here, we have 3 isotopes of hydrogen. Now, what makes hydrogen hydrogen is the fact that it has 1 proton. So whenever we have a single proton, that's Z equal 1, all right, that is by definition hydrogen because it will behave like hydrogen chemically. In other words, we can make water out of hydrogen, H2O, and we can make water in theory out of any of these types of hydrogen because it's still hydrogen. However, this is the normal type of hydrogen that most of the hydrogen is. It's just a single proton. But if we add a neutron to the hydrogen, now notice the hydrogen's atomic mass number is 2 instead of just 1 because there are 2 protons and neutrons total. Okay, this, by the way, is called deuterium, this hydrogen isotope. It's also called heavy hydrogen. And by the way, deuterium, or heavy hydrogen, is very useful. It's used in cooling and moderating nuclear reactors. This isotope of hydrogen here has 2 neutrons and 1 proton, and this is called tritium. And this hydrogen isotope is H3 because it has 1 to 3 total isotopes here. Three total nucleons in this nucleus. So the key thing here is that all of these are hydrogen, but they are different isotopes of hydrogen because of the different numbers of neutrons. Let's look at helium, which is the next element. This is the most common form of helium. Helium-4 is what you would find inside of a helium balloon, for example. It has 2 protons, the 2 red balls here, and 2 neutrons, the 2 green balls. So its total number of nucleons, its total atomic mass number is 4. So this is helium-4. But helium can also be found with just 3 total particles, 2 protons and 1 neutron. So this one has lost a neutron, and this is called helium-3. So what makes helium helium, though, is the fact that it has 2 protons. So all these isotopes of helium have 2 protons. One more example, lithium is the next element, element number 3. So lithium, by definition, must have 3 protons. So this is lithium-6 with 3 protons and 3 neutrons, and this is lithium-7 with 3 protons and 4 neutrons. Let's now turn to forces inside of the nucleus. As we've said, we can kind of think of the nucleus as this glob of protons and neutrons. And they're actually moving around inside here, but you can think of them as fairly tightly packed ball here of protons and neutrons. Now, what about the forces between the protons? Well, the protons, remember, are positively charged particles. So in this nucleus here, we've got a bunch of protons that are extremely close together. Remember, the whole size of this thing is somewhere on the order of 10 to the minus 15 meters. Okay, it's 50,000 times smaller than an atom. So these protons are so close to each other that they really are trying to repel from each other. Remember the electrical force between charges, when the charges are the same, they repel because opposites attract. So the question is, why doesn't this nucleus fly apart? What keeps it stable and held together in a tight ball like this? Obviously, there must be something holding it together. And it turns out there's another force in nature that's holding this thing together. This force in nature is called the strong nuclear force, and it's the strongest known force in the universe. All the interactions or forces in the universe can be described by these 4 forces here, and they're listed here in order of their relative strengths. So by far the strongest force is this strong nuclear force that holds the nucleus together. So let's give it a relative strength of 1. The next strongest force that even tries to get close to it is the electromagnetic force. And electromagnetic force is the electrical force or magnetic force, combined. And notice its relative strength is 0.01. That's only 1% of the strong nuclear force. In other words, this strong nuclear force is 100 times stronger than its closest competitor. So that's how powerful it is. Imagine if you had the strength of 100 humans, right? You would have superpowers, okay? You'd be able to lift up, tens of thousands of pounds easily, over your head with one hand. Now, after that, there are 2 more forces. One of them is called the weak nuclear force, and you can see it is very weak compared to the strong nuclear force, and it's involved with certain nuclear decay reactions, and we're not going to talk about the weak nuclear force in this course. But the 4th force here, which you know about, is gravity, and gravity is extremely weak when comparing it to, for example, the strong nuclear force. In fact, there are so many zeros here that I couldn't even fit them all in. There's something like 39 or 40 zeros here, meaning that gravity is extremely weak and feeble compared to this strong nuclear force here. Now, what is the strong nuclear force? Well, it's an attractive force that holds nucleons together. Now, what is a nucleon again? A nucleon is a neutron or a proton. So the nuclear force doesn't care if we have a proton or a neutron, and it doesn't care if the protons both have positive charge. The nuclear force is not an electrical force, it's a nuclear force. And so any neutrons or protons in close vicinity with each other will be very strongly attracted to each other. And this attraction between these protons here is, remember, it's 100 times stronger than the electromagnetic repulsion. So this attractive force is going to dominate and hold this nucleus together. Now, remember the analogy I made up here to if you had the force of the strong nuclear force compared to an ordinary human, you would have superpowers, right? But remember that every superhero, well, at least most of them that I know of, has a weakness, right? Superman has his krypton. So the nuclear force also has a weakness, and its weakness is that it only works within very short range inside the nucleus. So what this means is that in this glob here of protons and neutrons, these protons are all close together, relatively close together, and so they're going to be all attracted to each other, and that's going to overpower the electrical repulsion. But if we have a proton out here that's, kind of removed from the nucleus, it's far enough away that the nuclear force is not felt. So there's no attraction between this nucleus and this proton. So this proton, all it feels is the electrical repulsion, because this positive charge here is being repelled by all these positive charges here in the nucleus, and it's going to fly away. So the nuclear force is extremely strong and powerful as long as it's inside the nucleus and very close to the other particles. But the nuclear force does not work at all at distances more than about the diameter of a typical large nucleus. So if you're standing next to somebody on the sidewalk, you're not going to feel any nuclear attraction to that person. The nuclear force only works within the small vicinity here. The nuclear force creates a potential energy called the nuclear binding energy. And this is sort of analogous to the idea that whenever we have a force, there's often a potential energy associated with it. So, think about gravity. When we lift up a heavy rock over our head, that rock now has a lot of potential energy due to the gravitational force. So there's something sort of similar with the nuclear force. So what is nuclear binding energy? One way to think of it, it's the potential energy of the nucleus due to the strong nuclear force. Another way to think of it is it's a measure of how tightly bound the nucleus is. Remember that this ball of protons and neutrons is held together by this attractive force due to the strong nuclear force. And so this thing is bound together by this nuclear binding energy. Another interpretation of the nuclear binding energy is that it's the total energy needed to disassemble the nucleus. So in other words, if we wanted to reach in here and pull out each proton and each neutron one at a time, well, remember, they're attracted to this blob of protons and neutrons. So it's going to take energy to pull them out. We're talking about the strongest force in nature here holding this thing together. So in order to pull these things apart, we're going to have to use a lot of energy. So the total amount of energy to disassemble this entire nucleus is the nuclear binding energy. And kind of conversely, the nuclear binding energy is also the total energy that's released when the nucleus is assembled. So if we let these particles fly together, well, then it's going to ultimately release energy. It's kind of like when you take a rock and you drop it from above the ground, the rock falls, and that potential energy is converted into kinetic energy and ultimately into heat, which is finally released. So it's sort of the same thing here. When we let all these protons and neutrons come together, a large amount of energy is released. So there's something called, this is the total nuclear binding energy here. If we divide that by the number of nucleons, in other words, to count up all the protons and neutrons in here, and if we divide the total binding energy by the number of nucleons, then we get the average binding energy per nucleon. And this is something that we're going to plot in the next slide. So this is a plot here that we're not going to get into too much detail in here, but I just want to describe a couple of the features here because it helps explain some of the properties of the nucleus. So you can see this graph here is a plot of the average binding energy per nucleon plotted in this axis. And by the way, look at the units. This is uppercase M and then EV. So remember from the first chapter in this course, the uppercase M means mega, which means millions. And EV, remember, that's an electron volt, which is a unit of energy. So whereas atoms are usually associated with a few electron volts of energy, when we're talking about nuclear energy, we're talking about millions of electron volts. All right, so the nucleus contains millions of times more energy than the atom does with the electrons that are orbiting around the nucleus. So anyway, that's what we're plotting here, the average binding energy per nucleon in mega electron volts. And this axis down here is just the total number of nucleons, which remember is given by A, the atomic mass number. This is the total number of protons and neutrons added together. So over here, these are the small nuclei. And as we go to the right on this graph, we're getting to the larger nuclei. Okay, now let's, if we look at the graph, notice how it starts down here at 0 and it goes up and it peaks right around here, right around iron, and then it sort of slowly tapers off and starts to drop back down. So why is this? Well, it's actually not that difficult to explain, just using what we've already learned about the nucleus. Let's take, for example, hydrogen, regular hydrogen 1. So hydrogen 1, that nucleus is just a single proton, and there it is, okay? So a single proton has no binding energy because it's all by itself and there's nothing for it to bind to. Okay, so its binding energy is actually 0. All right, so that's our starting point. Now, if we take that proton and we add a neutron, all right, the neutrons are blue, the protons are red. Now we've got a proton and a neutron stuck together by binding energy. And you can see that there's about 1 million electron volts per nucleon here of binding energy because of that strong nuclear force. If we take another neutron and add it to it, we've still got hydrogen because there's one proton, but now there's 1, 2, 3. So this is hydrogen 3 or H3. And notice the binding energy is higher now. It's up to about 3 million electron volts. The reason for this is each one of these nucleons is bound to 2 more. If you think of these like powerful magnets, it's harder to pull a magnet away from 2 other magnets than it is from 1 other magnet. So these 3 nucleons here are held together much more strongly than these 2 are because there's more particles pulling on them. So as we go up this ladder here, we see that as we add more and more protons and neutrons to the mix, we get a higher and higher average binding energy. And it actually peaks out right around iron up here. Okay, and at this point, we've got, a total of 56, it looks like, protons and neutrons all stuck together, all pulling on each other very tightly. And as a result, there's almost 9 million electron volts of binding energy for each one of these 56 protons and neutrons. Now, something interesting happens, though. If we keep making the nucleus larger and larger, notice the curve doesn't go up anymore. In fact, the opposite happens. It starts to go back down, meaning this nucleus over here, this is uranium, all right, one of the largest nuclei. It has something like 238 protons and neutrons in it. This thing is not held together as tightly as iron. Now, why is that? Well, it has to do with the weakness of the nuclear force. Remember, as strong as the nuclear force is, it has that one weakness where it only works in short range. So here's the problem. The uranium nucleus is so large that these protons on the left side aren't even attracted to these protons on the right side because they're so far away. Now, it's all relative, right? This is only, something like 10 to 15 femtometers, which is 10 to the minus 15 meters. However, then the range of the nuclear force is less than that. So these nucleons over here are not attracted to the ones on the opposite side of the nucleus. So as we start to add more and more protons, remember the protons are trying to repel from each other. So that electrical repulsion starts to actually come into play, and it weakens this nucleus. It makes it so it's not quite as strongly held together. And that's why the curve actually drops as we get larger and larger. This is our last slide for this part of the lecture, and it's sort of a segue into part 2 of the lecture, which deals with radioactivity. So what we're going to end up with here is just a brief mention of what makes a nucleus stable. So it turns out that the stability of the nucleus requires a delicate balance between the number of protons and neutrons. If this balance is not correct, the nucleus becomes unstable and will undergo radioactivity to try to stabilize itself. So this is, again, we don't have to worry too much about the details of this graph. I just want to show you some of the basic features here. This is a graph of, this is neutron number, N, the number of neutrons plotted in the vertical scale, and this is the number of protons, Z, plotted in the horizontal scale. And all of these dots on the chart, there are a bunch of blue dots which represent stable isotopes, and there are many, many little red dots. In fact, there's so many of them, they're all kind of connected together. Now, on this, this graph here, there are 254 stable isotopes. So that's the blue dots. Notice they fall along a very narrow band here. So this means that these blue dots here represent stable nuclei isotopes that have the right balance of neutrons to protons. All the red dots are unstable nuclei, and there are more than 1,000 of them, and they don't have the right balance. These up here have too many neutrons, all right, and the ones down here below the curve, they have not enough neutrons. In other words, there's too many protons. So this is, this chart here shows us that in nature, we need to have the number of protons and neutrons balanced very precisely in order for the nucleus to be stable. And you'll notice that for a while, the line here of stability follows this black line here, which is N equal to Z. In other words, until you get about right here, all of these nuclei down here have the same number of protons and neutrons, and this is required for the most energetically stable configuration. What happens as we start going to larger numbers of protons, in other words, when we start going down the periodic table, notice the curve bends up. And this means that we need extra neutrons. Those neutrons are needed sort of like glue to help hold the nucleus together because all those protons are starting to pry themselves apart. So we'll talk about this more in the part 2 of this lecture, because the main idea here is that if a nucleus is not stable, then it's unstable, and then it's going to become radioactive. All right, and that's the main topic of part 2 of this video. So I will see you there shortly. Goodbye.